Hi, I'm Alistair, I'm a games designer, and in this video I'm going to explain how to create this pirate-themed escape room puzzle. So here I've got the wheel of a pirate ship, and what players need to do is to turn it in a particular sequence of clockwise and counter-clockwise rotations. Now, each time they move the wheel in the correct direction, an LED light illuminates on the map here to illustrate the path that this ship is taking across the high seas. If they turn it in the incorrect direction, however, those LED lights go out and they need to start again from the beginning. Now, if they input the entire sequence correctly, they will make their way all the way over here to Skull Island, and when they reach there, the treasure chest pops open and they can claim their prize from inside. Now let me show you how it works. So there's several different components you could use to detect rotary input. You could use a simple linear potentiometer like this, or you could use a rotary encoder or rotary switch. But here I'm using this AS5600 magnetic rotary encoder. And the reason I'm using this is because it is a completely contactless sensor. So if you've got fairly heavy props like this pirate wheel, and you've got to create a load-bearing mount and a mechanism that they're going to move on, you want to be fairly careful that your delicate, sensitive electronics are not going to get in the way or risk damaging or being damaged by that kind of mechanism. And the way that this sensor works is by detecting the direction of a magnetic field in its presence instead. It has no moving or mechanical parts at all, so it doesn't interfere with the mechanism used to mount the wheel itself. If I tell you a little bit more about how that works, I can actually remove the wheel from the front here. So I've got my wheel mounted on a simple wooden shaft. This is actually a 1-inch diameter broom handle which I cut down, and on the end of the broom handle there I've got a small magnet placed on the tip there. Now, unlike most magnets, this is a diametric magnet, and what that means is that instead of having the North Pole and the South Pole on the flat surface of the magnet, they're actually on opposite sides of the curved surface here. So as the wheel rotates, the magnet on the end of it spins round, and the direction of the magnetic field rotates as well. Now that is positioned just in front of the chip of the AS5600 there, and what that does is that detects the direction of the north pole of the magnet, and it provides the output via an I2C interface, which you can then read on an Arduino, or I'm using an ESP32. So here's a view from the side of the stand that's supporting the pirate wheel. Here I've got my AS5600 encoder module, and here I've got the mount that's just going to support the pirate wheel itself. These are actually mounts that were designed to hold a curtain rail up, incidentally. But they're just the right diameter for me to be able to slot in the wheel like this and push it through. And you do want that to be a snug fit because you don't want the wheel to be wobbling around laterally at all. You just want it to rotate. And it's quite important that the magnet stays centered over the chip here. You don't want it to wobble around. So for that reason, I 3D printed just this little cap here that's got the magnet in the middle of it. And that's going to make sure that the magnet stays directly in the middle of the wooden pole like that, and it's going to be positioned directly above the chip on the sensor. You can also see I 3D printed this little collar around the shaft here that mounts the magnetic chip away. That just holds it nice and straight and maintains it the correct distance away. This distance here can vary a little bit. I've got a distance there of about, I don't know, 6 millimeters or so, and I found that that works very reliably to detect the rotation of the magnet here. But crucially, you'll see there's absolutely no mechanical connection between the sensor and the wheel here at all. It is purely contactless, and that's why I think this makes that such a good choice of sensor for this particular prop. And then this is the view from behind. So as I mentioned, I'm using an ESP32, but in practice you could use pretty much any microprocessor to control this puzzle. There's nothing special about that. It's wired to the magnetic encoder up here via an I2C interface. And then I've got ground, VCC and a signal line here coming to a series of LED strips. And this are what illuminates to illustrate the path that the player has taken as they provide inputs there. And then I've also got a relay module down here, and that is controlling power from this power supply unit here to a maglock, which is in the treasure chest. And here is a better look at that treasure chest. So I made this out of old pallet wood. I'll be honest, I'm not actually much of a woodworker, so I'm pretty pleased with how it came out. It's certainly a functional chest. So what happens is while the puzzle is in progress, the 12 volt power supply is supplied to this maglock here. This is a 60 kilogram maglock, and that holds this bar in the top section firmly closed so that the lid stays shut. There's no handle on the front anyway, and this is actually pretty impossible to force open for as long as that maglock is energized. When the puzzle is solved, the ESP32 switches the relay off. That cuts that 12 volt power supply to the maglock, and then these gas struts, which I've mounted on either side, force the lid to open up. These are both 50 Newton gas struts. They've only got a short extension, but it's sufficient just to pop the lid up and then to also hold it in this raised position once the puzzle has been solved. As soon as players input an incorrect sequence on the wheel, that causes the maglock to energize again, so the puzzle is reset and the lid is closed and can be played again. And here's a wiring diagram to illustrate how the components are connected together. So I've got my ESP32 here, which is running the logic for the puzzle, and I'll show you the code for that in a moment. And it's got three main components connected to it. We've got the rotary sensor here, the relay, which is controlling the maglock, and we've got our LED light strip. Now let's start by looking at the AS5600. So I am connecting VCC here to 3.3 volts and ground to ground on the ESP32. And I'm using the I2C output, which means I also need to connect the clock, which is the SCL pin, and the data line, which is SDA, and they go to the corresponding I2C pins on the microprocessor. Now on an ESP32 the default pins are 22 for the clock and 21 for the data line, but you can actually adjust those in code to other pins if you want to. If you're using another microprocessor like an Arduino, that will be on pins A5 and A4 instead. Now the ESP32 is a 3.3 volt microprocessor, so these lines are going to be operating at 3.3 volts, which is also the supply voltage which I've connected to VCC. But according to the datasheet, the AS5600 will also operate at 5 volts. So if you're using a 5 volt microprocessor like an Arduino Uno or Nano or Mega, you should be able to connect directly to the I2C pins on that instead. Although I'll mention that I've not actually tried that, so that's just my interpretation of the datasheet. There's a couple of other pins on the sensor here as well. We've got a DIR pin. So the direction pin, that specifies the polarity of the output. So if you were to connect that to the ground line, the sensor will register a clockwise rotation of a magnet as a positive increment and an anti-clockwise rotation as negative. I've connected it to VCC instead, so 3.3 volts, and then it's the opposite polarity, so it treats anti-clockwise as positive and clockwise as negative. And the reason why I've done that is because in my setup I've got the sensor facing towards me, so it's kind of facing the direction of the pirate wheel in reverse. But in practice you can really do either, and you just have to adjust your code to match. There's also an out pin here which provides a PWM output of the reading. So if you wanted to, you could connect that to an analog input on your microprocessor and read that instead of using the I2C interface. But generally the ADC converter on a microprocessor is going to be less precise than the values you'd get from using the I2C, so I've just left that unconnected. There's also a pin labelled GPO here, although that's actually a mistake on the silkscreen. That should say PGO. And that's a pin which is used to put the chip into programming mode. But we're not going to use that, so you can leave that unconnected as well. Okay, now let's take a look at the relay. So this is a 5-volt relay module. And I know this is sometimes a cause for confusion about what that actually means. So when you describe a relay module as being 5 volts or 12 volts or 24 volts, what you're describing is the voltage required to operate the coil inside to make the contact flip between the normally open and normally closed connection. So because this is a 5-volt relay, I've taken the positive line here and connected it to V in, which is running at 5 volts on my ESP32. I've also got the grounds connected as well. And the signal line I've connected directly to a GPIO output. I'm using pin 5. But as I mentioned earlier, that's running at 3.3 volts. But that's absolutely fine. The signal line will trigger a 5-volt relay even if it's only outputting a high signal of 3.3 volts. It's the power supply that needs to be 5 volts, not the signal line. So that's always, some people find a bit tricky. And then on this side, the load side of the relay, we've got a 12-volt supply. So again, even though this is described as a 5-volt relay module, it can actually handle loads on this side up to 30 volts DC or 250 volts AC at 10 amps. Now, I'm using a 12-volt maglock. That typically draws, I don't know, around an amp in current, depending on how long the bar magnet you're using is. So I've got a 12-volt DC supply here that's rated at 3 amps, which is plenty enough. It won't actually use that much. And when the ESP32 sends a signal down this data line here from GPIO pin 5, it causes the contact inside the relay to flip over, which either makes or breaks this circuit here. That's going to connect this 12-volt DC supply to the maglock and energize it, or alternatively it's going to break this connection here, in which case the maglock will release and the treasure chest will open. And then finally, the third component in our circuit is this LED strip down here. Now, once again, we've got an LED strip which is WS2812B, which is operating at 5 volts. So we've connected the 5-volt line here to my 5-volt net, which is also going to the relay module here. But we can still use a 3.3 volt pin, so I'm using GPIO27, on the data line to send the data into the strip. The way that these LEDs actually work is that inside each LED there's actually a little chip that sends the signal to the next chip in the line. And they themselves operate at 5-volt logic. So even though we're sending a 3.3 volt signal into the first LED in the line, from that point onwards, each LED is actually going to send a 5-volt signal to the next one anyway. It's going to act as a logic level converter for us, this first LED. As always, when we're using an LED strip such as this, I've put a capacitor across the power lines. You want that to be quite close to the first LED as possible. I'm using a 1000 microfarad capacitor, and that's rated at least 6.3 volts. That can actually be greater than that. You can use 10 volts if you want. Just to be clear from the diagram here, so this is connected. I've got the negative side of the capacitor going to ground, and the positive pin here is going to the 5-volt line. It's actually straddled across the data line there. It's not connected to it, but I'm afraid it was a bit tricky to depict that using fritzing, but that's what's going on here. And finally, I've got a 330 ohm resistor. That's just connected in series on the data line between the GPIO pin here and the first data in on the strip. So that is all the wiring. Now let's take a look at the code that's running on the ESP32 itself. So the code starts off by including two external libraries. The first one is the AS5600 library that was written by Rob Tillart. Rob is a prolific Arduino developer who has written libraries for all sorts of sensors and components, and he's written a library that does a lot of the basic interfacing with the encoder for us, so I'm very grateful for that from him. And then we're also using Fast LED, which I've used lots of times before. This is a great library used for interfacing with lots and lots of different sorts of LED strips, not just the WS2812B which I'm using, but you can use it for all sorts of other programmable LED effects as well. Then we go on to the constants. So constants are variables which are going to retain their value throughout the duration of the sketch, and I tend to use these either for defining the way in which hardware has been set up, or for certain features which are going to remain static throughout the code. So the first thing is we'll tell the code where we have connected our various components to. I've connected my relay output to GPIO pin 5. The LED data output is connected to GPIO pin 27. And that matches the wiring diagram I just showed you, but if you've connected yours to other pins instead, you simply edit the values here to reflect that. I am using 12 LEDs in my LED strip, and that also corresponds to the number of inputs I'm going to expect the player to make. And generally speaking, I would expect those values to always be the same, but I've kept them as separate variables just in case you want to edit that behavior. Maybe you want to have a longer sequence of inputs, but only for players to receive a confirmatory LED light up every 2 or every 3 strips or something like that. So in theory you could edit those to be different values, but I've kept them to be the same, so you're currently getting one LED lit up on the map for each correct input. And then this array here is actually defining the sequence that we want players to make to solve the puzzle. And each one of these values in the array is either a -1 corresponding to a counterclockwise rotation, or a +1 corresponding to a clockwise rotation. Now again, if you'd wired the polarity of the sensor, so that DIR pin, if you'd wired that to ground or to 3.3 volts the other way round, you'd need to swap all these minuses and positives over. That's the only difference you'd really need to make in the code. So the pattern I've defined here, I'm going counterclockwise, counterclockwise, clockwise, clockwise, counterclockwise, clockwise. I'm kind of alternating it a bit to make it what I think is an interesting sequence that players need to enter. The next one is the number of different, and I've called them segments on the input. So we've got a completely continuous input that can be rotated 360 degrees. We're reading that with a 12-bit encoder that's going to give us 4096 values back. And we want to have a way of kind of quantizing that 4096 down to a more manageable number of inputs that the player can perceive. Now, the pirate wheel I'm using has got 6 spokes on it. So I'm interpreting a rotation from one spoke pointing up to the next spoke pointing up to be one segment of the wheel. So that's what I mean when I've written 6 here. If you were doing this on a compass instead, let's say, that has windrow's directions of north, northeast, east, southeast, south, that would be 8 segments that you might want to enter. Or you could do it on a clock face, which has got 12 segments. You can actually have lots and lots of different rotary inputs that are logically divided into different positions around the face of the wheel. But I'm using 6 because that corresponds to the spokes on my pirate wheel. And now that we know the number of segments we're dividing the wheel into, we can also work out how many values returned from the encoder do we get in each one of those segments. Well, that's going to be a straightforward sum. We simply divide the total number of values that we get in a complete rotation, which is 4096, and we divide it by the number of segments we defined here. And that's going to remain constant again. And finally, we're going to assign a threshold, a kind of a tolerance value of how close this value needs to be to the measured value to decide whether the wheel has been turned a full segment or not. Initially, I set this puzzle up to divide the entire wheel into logical segments. So imagine a Trivial Pursuit piece that has been divided into 6 segments, or a roulette wheel. Every time the wheel stops, you can be certain of an exact segment that you are landed in. But the problem with that is if the wheel was turned to lie exactly on the boundary between 2 segments, you'd potentially have a situation where it was flicking backwards and forwards very quickly between them. So a little bit like debouncing a button input, you want to have a sort of a dead zone within which you're not registering a change between values, and that's what I'm using this threshold for. If the wheel has been rotated to the next segment round, and we'll show you in a minute how we determine which segment you're in, and if it is pointing at that segment within this allowed tolerance, then we're going to register it as a rotation. And we'll work out whether that rotation was clockwise or anti-clockwise and compare it to the sequence up here. Now, this value here is measured in the readings that we return from the encoder. There's 4096 of them, so a threshold of 200 corresponds to about 5 degrees either side of the intended segment pointing up. You might want to adjust this value depending on things like the size of the wheel that you're turning and how precise you want players to be. But this is what I found works out as pretty well for me. So that's just going to allow you to fiddle with the sensitivity, effectively, of the input that's allowed from the players. We'll move on to the globals. So in our globals section, which are variables that are going to be shared between all the subsequent sections of code, we'll define an object which is from this library, which we included from Wrapup up here. And we're going to use that to access the functions of the rotary encoder. We'll define an array of all the RGB values that we're going to send out to our LED strip, and that array is going to have num LEDs, number of elements in it, because it's going to have one RGB value for every LED. We'll also keep track of what step of the solution the player is currently up to, and we'll initialize that with the value 0. So because arrays are 0 indexed in C, what that means is to start off with, the first input we're expecting the players to make is going to be the 0th element of the solution array. So we want them to enter a -1 to start with. That's counterclockwise. Every time they get that correct, we're going to advance the current step one more down the sequence, and we're going to compare to the next value until we get to the end of the array. We'll also keep track of what segment of the wheel, so of those 6 sections which I defined up here, which one are we currently pointing at and which one were we previously pointing at as well. We're going to use that to decide whether the wheel was turned clockwise or anti-clockwise. Then we get on to the setup function. So the setup function is run once when the code first starts up and the board is powered up. We'll start up a serial connection. This isn't actually used for the puzzler tool, but it's helpful to always use this in any code, I find, just because when you come to develop it, to program it, to test it, or to add features later on, it's really useful to just be able to quickly throw in something like these lines down here to say what's going on in the code. This will output a message to this serial connection, and it means you can plug in a USB cable to a laptop on site or something like that and see exactly what's going on with the puzzle. So even if you don't intend to use a serial connection as part of the logic itself, I still find it very useful to have one set up. And the first thing it will do is it will actually output this file name, so the script that this controller is running, and also the date at which it was last compiled as well, so we know what version we're running of the code. Then we will add our LED array into a fast LED object, so we'll be able to set the RGB values of all of the LEDs in our strip after this. So we'll define the type of LEDs we're using. These are WS2812Bs, also known as neopixels sometimes. We'll say the pin, the GPIO pin on the processor that we connected to the first data input in the strip, and also the byte order. So we normally refer to RGB values. That's the most common way you'll see color data encoded as a series of 3 bytes, but these strips actually use green, red, blue byte ordering. And if you find that when you're expecting your strips to light up red, they actually go blue, or if you expect them to be orange and they're purple or something like that, a likely reason is probably because they are using a different byte ordering than you were expecting. Now, as it happens in this particular code, we're only going to be lighting up the LEDs white anyway, so you won't actually notice any difference, but that's what that statement there does anyway. And we'll give it a reference to the LEDs array. That's what we defined up here. And we'll say how many elements there are in the array. There are num LEDs elements in that array. We'll clear the array, so we'll start off with all the LEDs off, and then we'll just actually send that array to the strip itself. All of the assignments of setting values in this array, clearing the array, setting things to a certain color, they actually only take effect when you then send that data out to the strip, and that's what the show command here does. So we'll actually see that again in every iteration of loop a little bit later on. Every time you change an LED value, you actually want to make sure you send the new value out to the strip as well. We'll initialize our relay, so we'll declare that the relay pin, the pin that's going to the signal line on our relay, is an output, and we'll initially write a high signal to it. That's going to lock the maglock and keep the treasure chest closed. And then we'll initialize the sensor. Now, the AS560 library has a handy begin method for us. That will do everything to start up the I2C interface, to connect to the sensor, and it will just check that it is online correctly as returned by this isConnected method. So we'll call that, and we'll just dump data to the serial monitor just to make sure we were able to establish a connection. It's pretty straightforward. There's not very many settings you have to change. The only one I've included, though I've commented it out here, is this set offset function. Now, this is quite useful. If after you've built your prop and you've glued your diametric magnet onto the end of your rotating shaft, you find out that you didn't sort of line it up level, you can add an offset value to all the readings that are returned from this object here. So this is measured in degrees. Let's say that you intended a certain direction to be up, and you've actually mounted the magnet 90 degrees out from that. You could put -90 here, for example, and then your readings would return as you expected them to be later. So I've just left that in just because you might find it useful if you come to build this prop later. And finally, we'll take a first reading to determine what segment we are in when we first load the code up. We'll get that by reading the angle that is returned from the AS5600 object. We'll get that with this read angle function. We'll add on to that the number of values you get in each segment divided by 2. Now, the reason for this is a little bit hard to explain. If you imagine a clock face, and we've got the 12 of a clock pointing up, and if I was to approximately say what time it is by looking at the hour hand of a clock, to the nearest hour, I would want to know whether the hour hand was closer to the 12 than it was to the hours on either side of it. So basically, was it greater than 11:30, or was it less than 12:30? And the way you get that is by adding on half of the value of the segment to the correct value you're looking to read. Because we're saying we want it to lie halfway either side. The reason for the modulo operation, however, is because we might be wrapping around, as indeed we are, every time we go over the top of a clock. So as you move clockwise around a clock, you generally increment until you get to the 12 to 1 jump, where you suddenly jump down again. Likewise, if you go anti-clockwise around a clock, you generally decrease and you go from 1 to 12. And to handle that kind of jump over a wrapping around point, we're going to take a modulo operation. And I've written the function that's going to do that here. C, on the language on which Arduino is based, has a built-in modulo operation which you can use by just using the percentage sign, but that doesn't handle negative values in the way that you'd expect them to. Modulo is not actually mathematically defined for negative values, and different programming languages use them in different ways when you attempt to do a modulo of a negative number. But the way which I want it to work, which I think is the way that most people expect it to work, is defined here, and that's going to come in useful when we are determining whether the wheel has been rotated clockwise or anti-clockwise. Okay, so then we get onto our loop function, and the loop function accounts for the whole of the rest of the code, and this is just going to run over and over again for as long as the processor has got power going to it. So on every iteration through loop, the first thing we do is we take the raw reading that we get from the sensor right now. So we're going to call the read angle function, and that is going to assign a value from 0 to 4095 to this variable called raw reading. Now, having got that, we then need to work out, well, which segment are we currently in based on that reading. So we're going to loop over all the segments. We're going to compare the difference between the raw reading that we've just taken and the midpoint of each of the segments around the wheel. So if we've got 6, as I have in this case, segments around the wheel, I'm going to take the values that are in the first segment, then the values that are in the second segment, third, fourth, fifth, etc. I'm going to loop around all of the segments in the wheel, and I'm going to compare the absolute difference between the reading I've just taken, the midpoint that I am expecting that segment to have based on here, and I'm going to see whether that is less than the threshold that we defined at the top of the code here. So this is a slightly sort of complicated way of looking at what this function does, but it really makes sense when you think about the analogy I was just describing in terms of looking at a clock face. If I told you to tell me what is the time to the nearest hour, you'd look at the clock face, you'd look at all the numbers, you'd see where the hour hand was pointing, and you'd simply say, is the hour hand pointing at any given hour within the allowed threshold? And again, we're using the mod function here, which was defined up here. This is to account for the fact that the 1 to 12 wraparound, or the 1 to 6, or the 1 to whatever it is, the fact that every time we go around a complete rotation, we jump back to the beginning again. We don't consistently increase as we go clockwise or not. If it is within the allowed threshold, we will say that we are currently looking at that segment, and then we'll break out of the loop. Now, if the segment that we're now in is different from the last segment that we recorded, well, then we know the wheel has been turned. So we need to decide which direction it's been turned. And we do that by comparing the current segment we're in to the previous segment. We take, once again, the modulo operation for this wraparound, and we'll see, has the number of segments that have been turned less than the total number of segments on the wheel divided by 2? If it is, we've gone anti-clockwise, and if it's not, we've got clockwise. Now, I could try and explain why this is true. So, if you go from 6 to 7, then your current segment is 7, your last segment was 6, so the difference between them is 1. If we take the modulo operation, that's still going to be 1, and 1 is less than half the number of hours on a clock face, which is 6. So 1 is less than 6, so we have gone clockwise. And if we went from 6 to 8, or 6 to 9, or 6 to 10, or 6 to 11, that would still be going clockwise. But as soon as we went from 6 to 2, let's say instead, we then have our current segment being 2, our previous segment being 6, so we've now got -4 here. But when we take the modulo of -4 compared to the number of segments, which is 6, we get 2, and 2 is less than half the number of segments on the clock face, which is 6. So as a result, we've gone anti-clockwise. Now, this is tricky to get your head around, but essentially what we're saying is that we expect the players to have always taken the shortest route around the clock face from one position to the next. And if that involved going clockwise, we'll record it as a 1. If it involved going anti-clockwise, we'll record it as a -1. And then we'll need to say, well, was that the correct input? We do that by comparing the direction to the step that we're up to in the solution array, which was up here. And we're going to incrementally just step through this in turn according to the current step that we're up to. If players did input the correct direction, then we'll dump out a little serial message, say, fantastic, they got it right, let's go on to the next one. We'll light up the next LED in the strip to be white. We'll advance the current step counter. And if, having incremented this, we have now reached the total number of steps in the puzzle, then what we can do is we can write a low signal to the relay pin. That's going to deactivate the maglock and the chest will pop open. However, if at any point the input does not match what we're expecting the next value in the sequence to be, we will instead reset the counter all the way back to the beginning. We'll clear all the LEDs, blank them out, and we will relock the maglock again. So that's a way you can quickly reset this puzzle as if you're a games master as well. Simply make any wrong input at any point in the sequence, we'll reset the puzzle, clear the LEDs, and we'll lock the treasure chest as well. So that's very quick on a reset mechanism. And finally, what we need to do is just to update the last segment variable with whatever we're looking at now, so that the next time we step through this loop here, we are then comparing it to the new last segment. Then all we need to do is send the updated array of LEDs to the LED strip, and we'll just put a little delay there just to slow the rate down, just to reduce power consumption really. We don't need to belt through this code at the total speed available to the microprocessor, so we can afford to put a little delay there just to slow it down. So that just about brings me to the end of this video, and there's just a few final things I'd like to mention. Firstly, I did not create this pirate wheel. I'd love to say that I did, but actually I bought it online and then I 3D printed this skull and crossbones and mounted it on the front. But of course, you don't have to use a pirate wheel for this puzzle at all. You could use this same code and setup for detecting any continuous rotary input. And the AS5600 contactless sensors I demonstrated are particularly good for detecting rotations of big props like statues or the safe dials that unlock a bank vault. Now, detecting the angle at which the input is currently pointing is actually pretty easy. The thing that made the code slightly more complicated was having to deal with the issue that you've got a continuous input, but the angle jumps back to 0 every time you perform a complete rotation. Now, if you wanted to use slightly simpler code, you could simply detect the angle at which the wheel was currently pointing and ignore the calculation of the direction it might have turned to get there. Now, as always, I will upload the code I demonstrated along with the wiring diagram, the STL file of the 3D mount I created onto my Patreon page. And I want to say thank you to all my Patreon donors for enabling me to create these tutorials each month. I really appreciate your support. If you like the tutorials I create here, please do go over and check it out, where you can download the resources used for all of the escape room tutorials I've created over the last 5 years. But if you don't want to, or if you're unable to support me, that's fine. I will continue to provide these tutorials for free on YouTube anyway, and you can subscribe to this channel to get new videos each month. Finally, if you have any comments or suggestions, please do write them down below, and I look forward to seeing you next time. Okay, cheers, bye.